Hello students, this is your professor Sara Beck speaking, and I have another demonstration to help you understand the Coriolis effect and how it differs in the two hemispheres. Hopefully you just saw the last video activity, which was filmed in the classroom, and hopefully you've already also seen the National Geographic merry-go-round Coriolis effect video on Edpuzzle, and also the very first Coriolis effect video that was on Edpuzzle. So you should have seen 3 videos by now. And now here we are in my living room to demonstrate another aspect of the Coriolis effect using this record player or turntable for playing vinyl records. So we have a little assistant today. We've got Mr. Penguin here, and we're going to review a couple of concepts that we've already learned. So we're going to set Mr. Penguin here near the center of the turntable. And when we start spinning, we can see that the penguin is having to complete a journey, a circumference of around 3 inches. We've got an inch diameter here. And the penguin is right now going about an inch per second. So you can see the rotational velocity is considerably slower than, say, if we move him all the way out. I'm going to pause this. All the way out to here, where now the penguin has to complete a circle with a diameter of about 10 inches, which means that the penguin is now going approximately 10 inches per second instead of 1 inch per second. And we learned this earlier, but this is just to remind you that along the equator, which is at 0 degrees latitude, you, or whatever portion of the Earth, is going to have to make that entire journey, all of the entire circumference of the Earth, in just 24 hours. So being around 24,900 miles circumference, that would be about 1,000 miles per hour that you'd be zooming around if you were at the equator. Now, if we were to compare a couple of different things here, Maricosta College is at around 33 degrees north latitude. So we'd be moving closer to if we imagine this is the North Pole here. And at Maricosta College, at 33 degrees north latitude, we're moving at around 870 miles per hour. So still very fast, but not as fast as the 1,000 miles an hour that we'd be going along at the equator. If we were to move further north, up to, say, Seattle, that's about 700 miles per hour. And then if we went up towards Anchorage, Alaska, even closer to the North Pole, we'd be moving at around 500 miles per hour. And then if you were to stand entirely on top of the North Pole, which we can't do right here, then you'd be actually just moving at 0 miles an hour, just really turning around on your own axis, but not covering any mileage, or in this case inches, in your daily path. So let's bring this back to some of the other things I wanted to show you here. So let's say we've got Penguin here, right? Mr. Penguin is hanging out near the middle, and we're going to say that Mr. Penguin, if he were to throw an object, or let's say that we have winds or currents moving away from Mr. Penguin, it's going to be traveling from areas of lower rotational velocity to higher rotational velocity. And this is pretty similar to what we saw in the National Geographic video, where we had our 4 people on the merry-go-round and they were trying to throw the ball across, and we saw that there was a deflection to the right in that case. And you were also asked to predict what would happen if the turntable, or in that case the merry-go-round, were to rotate the opposite direction. So we're going to look at these kind of things now. So our penguin here is hanging out in the southern hemisphere. So if you recall from the last video, if we were out in outer space looking down on the penguins at the South Pole, as we are now, we would have which kind of rotation? Would we be going clockwise or counterclockwise? So hopefully you recall that in the southern hemisphere, if we were looking at the South Pole from space, the Earth would appear to be rotating in a clockwise fashion. Now, as we know from the last video, this is just from your perspective. If we were out in space looking down at the North Pole, it would appear to be rotating counterclockwise. Now, of course, the entire globe is rotating from east to west, or excuse me, west to east, west to east. We do have these differences in the hemisphere in terms of how it looks from the perspective of outer space down to one of these poles. So again, we're looking at the penguins at the South Pole, and we have a clockwise rotation. So what I want to do now is with my penguin here, if I were to draw a straight line, kind of like throwing the ball in the merry-go-round example, if I were to draw a straight line, just dragging my pen down like this towards me, we'll see what happens here. So I'm going to just do a couple practice runs so you can tell I'm just going a straight line. Start the turntable again. That wasn't very good. Let's try again. Okay, so sure enough, if we were to look from the perspective of the penguin, put the penguin over here at 1, from the perspective of the penguin, everything that he is throwing or is viewing is moving to his left. Maybe it'll help if I turn it around this direction. If the penguin is looking away, you can see sure enough the objects, or in this case my marker pen, is deflecting to the penguin's left. Now, what if we tried something different? What if we put the penguin on the outside and we were looking about objects going towards the South Pole in this case, moving from higher rotational velocity to lower rotational velocity? So the Earth is still spinning the same direction. We're in the southern hemisphere, so that's clockwise. But if I were to try to repeat this one's a little more challenging, from the outside to the inside. Do a couple practice runs here. Okay, so now penguin's on the outside, so I'm going to just bring him around here. Sure enough, looking from the perspective of the penguin, it still appears to be going to the left. So it doesn't matter if we're going towards or away from the poles. Anywhere in the southern hemisphere where we have this clockwise rotation, objects are going to appear to bend to the left from the perspective of the viewer, in this case, the penguin. So in this case, we are looking at the southern hemisphere. It's not a very good Sharpie. There we go, hemisphere. So the Coriolis effect appears to make things deflect to the left in the southern hemisphere. Now let's try in the northern hemisphere. So now we're in the northern hemisphere. Let's see what happens to Mr. Penguin. Now, I'm not going to use Mr. Penguin in this case because penguins live in the southern hemisphere, not the northern hemisphere, so that would just be silly. So we might as well go full silly and just have a Triceratops instead. So now we've got this Triceratops hanging out in the middle, and I'm going to change the direction so that now we have a counterclockwise rotation. So again, I'm going to try to draw from the inside to the outside, the inside being the North Pole. So we are out in outer space looking directly down at the North Pole. And I'm going to do a couple practice stripes. And there we go. And I'm trying my best to keep these lines straight. So if we were to look here, from the perspective of the T-Rex, things appear to be bending to his right. Now if we try the same kind of thing as we did before, I'm sure you're expecting a similar result, but we'll try again. So now if we're trying to go from a faster rotational velocity on the outside to a slower one in the middle, and try to draw a straight line again. Oops, I knocked over the Triceratops. Okay. So sure enough, he'll get up here. He's okay. If we were to get a better line, it looks like things are deflecting to the right in the northern hemisphere. So I hope that this demonstration helped show you a few things. When you move from areas of a faster rotational velocity to slower rotational velocity, or vice versa, you really just have to be moving into or out of areas with differing rotational velocities, which are entirely controlled by your latitude, which is how far north or south you are from the equator or the poles. Then you're going to have this deflection. It's an optical illusion. In fact, as you saw, I'm capable of drawing curved lines, but I was only drawing straight lines. They just appear to be curved because we were moving from one area of a different rotational velocity to another. So I hope this helps sort some things out.